Hello, welcome back. We're looking at electromagnetic induction. And what we saw so far is that Faraday did some experiments in 1831, and he was able to show that by moving or changing a magnetic field, he was able to generate an electric current. Then we saw that this was due to the fact that moving a conductor through a magnetic field generated a motional EMF, and that if we then had a closed circuit, we could actually generate a current. So now what we're going to look at is what it really means to have a magnetic field going through our loop. What does that mean? And then we're going to use that to look at what's called Lenz's Law, where Lenz's Law tells us what the current will be due to how much of the magnetic field is going through our loop. So let's start by looking at an idea of what happens if we have a sheet going through a sheet of metal going through a magnetic field. So one other thing that happens, another side effect of the fact that when we have a sheet of metal that is being pulled through a magnetic field. So here we have a magnet on either side, the magnet with the North Pole on one side and the South Pole on the other, and we're pulling this conducting sheet, this sheet of metal, we're pulling it through in this in the direction to the right here. And we see that as we pull it through, we get Q, V cross B will end up giving us a motional EMF, which will then cause currents to start happening inside our metal sheet. And in this case, it's a big metal sheet. And so instead of just having a current going around a loop, we actually have currents inside the metal sheet. And these currents, as we saw, they will then have a force, a magnetic force equal to ILB. And so we saw that that is always equal to the opposite of the direction of the motion. So it's always equal to opposite the direction of the motion. And so this becomes a retarding force. So consider pulling a sheet of metal through a magnetic field. Two whirlpools of currents begin to circulate in the solid metal. These are called eddy currents. So these currents that start to circulate here, we call these eddy currents. And we know that the magnetic force on the eddy currents, in this case, is always going to be opposite the direction of motion. So that is a retarding force. And so this is what we can use. It's known as magnetic braking. So now let's look back at some ideas that we've already talked about, and that's the idea of flux. So we looked at electric flux before, and now we're going to look at magnetic flux. So let's come back to our basic definition of flux. So basic definition of flux, if we imagine holding a rectangular wire loop of area, A equals AB, in front of a fan. So we picture our loop that we're holding up in front of our fan. The volume of air flowing through the loop each second depends on the angle between the loop and the direction of flow. So we know that in that case, no air will go through the same loop if it is parallel to the flow. So if we have our loop just perfectly parallel to the flow, there will be no air going through. So it will be no flux. And the flux will be a maximum when it is perpendicular to the airflow. And we know this occurs because the effective area is going to be greatest at the angle when the rectangular wire loop is completely perpendicular to the flow. So the effective area, as seen facing the fan, will be the A effective equals AB cos theta, which in this case will be A, where A is the area, right? A is equal to the area, A times B, the sides of our loop. Cos theta. Here's the image of that. So here's our fan, and we see that if we take our wire loop and we put it in our fan and we change the angle of that wire loop, it's this angle that's going to determine how much of the air actually goes through our wire loop. So the flux in this case, we define our flux as the amount of air passing through the loop per second. So let's look at the magnetic flux through a loop for different situations. So at theta equals 0, where we have a perfectly parallel loop, perfectly perpendicular to our magnetic field. In this case, it's perfectly perpendicular to our magnetic field, and we define the normal to our loop in this direction. So these are perfectly parallel. It's the normal to the loop that is perfectly parallel to our magnetic field. So theta equals 0. And we know that the cosine of 0 is 1. So that's the greatest flux that we can have. Now, in that case, that would look like this. If we have a loop that is perpendicular to a field. And so that will have the maximum number of arrows that can pass through. So these are little arrows that we're shooting through, and we can have our max number of arrows that can pass through if we have our loop perpendicular to our field. Now let's imagine that our loop instead is rotated through some angle theta. So here's our angle theta. It's been rotated through some angle theta here. And so now we have a much smaller effective area. And so we have fewer arrows that are going through our loop. And of course, the other extreme example, if our loop is in fact rotated completely 90 degrees, in that case, it's completely, no arrows will pass through. So we have 0 flux in that case. So here's our loop of area A. We've defined our normal to our loop, the normal vector, vector A, and the area vector is always perpendicular to the loop, and its magnitude is the area of the loop. So let's define an area vector A to be A n hat to be a vector in the direction of perpendicular to the surface, with the magnitude A equal to the area of the surface. Vector A has units of meters squared. Now let's look at this again. So here, the magnetic flux measures the amount of magnetic field passing through a loop of area A if the loop is tilted at an angle theta from the field. So here is our angle theta between the normal, which is our A, our normal to our loop, and the field lines. So the magnetic flux through the loop in this case is, again, we're using the flux symbol here, sub m. In this case, it's magnetic flux. It'll be A dot B. The angle theta between A and B is the angle at which the loop has been tilted. So we see that again, the flux is going to be A effective times B, which is AB cosine theta. Now the units that we use for magnetic flux is called the Weber. So the Weber, somebody else got named for a unit here. And our Weber is equal to 1 Tesla meter squared. So that's, of course, the magnitude B, that magnitude of the magnetic field B will be Teslas, and the magnitude of the area will be meters squared. And so we end up with 1 meter squared. And so we end up with 1 Tesla meter squared for our Weber. Now, that's the magnetic flux. So now let's think about what it means to have a magnetic flux in a non-uniform field. So in this field, we see that there are many more X's on the right side over here than there are on the left side. And so we have an increasing field strength from left to right. So if we have a small area, dA, right here in the center of our loop, the flux through this little area will be d phi is equal to B dot dA. So that's what we're looking at here. So the figure shows a loop in a non-uniform magnetic field. The total magnetic flux through the loop is found with an area integral. So we need to add up all these little pieces dA throughout our loop. So we see that the area of the loop, we're going to integrate over the entire area of the loop here. And that'll be B dot dA, where we're integrating over the entire area of the loop. And since the magnetic field in this case is changing, we have to look at each place where we have to add up all the little pieces, because it's not the same for each piece. So those are the ideas of how we look at magnetic flux. Now that we see how we can look at magnetic flux, let's now apply that and understand something called Lenz's law. So Lenz's law shows us that a bar magnet, for example, that's pushed towards a loop here, Now it increases the flux through the loop, right? Because the magnetic field points from the north to the south. So we have a magnetic field pointing downward. If we push that magnet toward the loop, we're going to increase the flux in through the loop. So now what we want to figure out is which direction is the induced current. So we know there's an induced current, and we saw it when we were taking our magnet and putting it into our coil of wires, and we saw that we did get a current, and we saw the direction wasn't always the same. If we put it in, we got one direction. If we took it out, we got the other direction. So we want to figure out what is the direction of the current. We were looking at the voltage, but that was also giving us an indication of the direction of the current. So now let's look at how we can figure out what is the direction of the current. Well, what Lenz's law tells us is that there is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. So we saw that we didn't have any sort of current. We didn't see the light bulb light up at all when we had our magnet just sitting there, even inside the loop. But if we move the magnet, then we do get the light bulb will light up, and we do see a change on the voltmeter. Now, the direction of the induced current is such that the induced magnetic field opposes the change in the flux. So it's going to try to oppose the change in the flux. It's going to try to keep it the same. So let's see if we can figure out how we might apply this. So here we have Lenz's law. So pushing the bar magnet into the loop is going to cause the magnetic flux to increase in the downward direction. So here we go. We're pushing our bar magnet into the loop. So the flux through the loop increases downward as the magnet approaches. So the closer we get, the flux is increasing downward. So the flux is increasing downward. Now the loop needs to generate an upward pointing magnetic field to oppose the change in the flux. So to oppose the change in the flux, which is what Lenz's law requires, the loop itself needs to generate an upward pointing magnetic field. So we want to get an upward. So we want B induced to be upward. So if we want B induced to be upward, we're going to take our right hands and we're going to say, our right hands, we're going to want upward. We'll take our fingers, we'll curl around, and our fingers will curl around, in this case, in a counterclockwise direction. So by the right hand rule, a counterclockwise current is needed to induce an upward pointing magnetic field. So the induced current ceases as soon as the magnet stops moving. So that's only while the magnet is moving that we get this induced current, and it will be in the direction that will counter the change in the magnetic field. So now in this case, pushing a bar magnet away from the loop will cause the magnetic field to decrease in the downward direction. So now it's like what we saw in our first experiment when we took the magnet back out of the coil of loops. And we saw that in this case, we are now decreasing our magnetic field. So our magnetic field is down, but it's decreasing. So now, as the bar magnet moves away from the loop, we are decreasing. So B magnet is decreasing in the downward direction. So now we need to have, to oppose this decrease, we need to have an induced magnetic field that is downward. So that will oppose it because it's decreasing in the downward direction. So we take our right hands and we want to point our thumbs down, and we see that our fingers then curl around in a clockwise direction. So in that case, downward flux due to the magnet is decreasing. So a downward pointing field is needed to oppose the change. So a downward pointing field is induced by a clockwise current, which we saw from our right hand rule. All right, let's go through a couple different examples of these. So the first one, very simple. If we just have a magnet, like we saw with our experiment, if we just have a magnet that's just sitting there, it's not moving, it's just sitting there. There is a magnetic field because we have a magnet, but it is steady. And so in this case, we have a magnet. We're going to have it below here. So we have our magnet like this, north here, south here. And in this case, it's not moving. So there is no induced current. There's no change in the flux. So there's no induced field. So there's no induced current. Now, in this case, we have the magnet is up and increasing. So we're taking our magnet and we're moving it upward. So if we're moving our magnet upward, we're increasing our magnetic field. So now to counter that, the loop will have a magnetic field in the opposite direction. So that will be down. And we take our right hands and we turn them around and we say down means that we must have a clockwise current. So the induced current in this case is clockwise. Now in this case, we have a magnetic field that again is up, but this time it's decreasing. So it's up, but it's decreasing. So in this case, our magnetic field points up, but the magnet's getting pulled away from our loop. So now our change in flux is downward. So our induced field needs to be upward. So our induced field needs to be upward in this case. And we take our right hands and we put our thumbs in the upward direction and we see that we get a counterclockwise current. Now in this case, we have our magnet above here, or we could have it the other direction. And in this case, there is, if it's down and steady, so we have a magnetic field that's down and steady, there is no change in flux, there's no induced field, and there's no induced current. Now, if we have our magnet down and increasing, so increasing in the downward direction, now our change in flux will be downward, so we must have an induced field that is upward. So we take our right hands and we point our thumbs up and we see that our induced current is now counterclockwise. Now, let's say that we have our magnetic field is down, but it's decreasing. So the change in flux in this case, this is the stranger one, the change in flux in this case, even though the magnetic field is down, it's decreasing. So the change in flux is actually in the upward direction. So even though the magnetic field itself is pointing down, it's decreasing. So the change in flux is actually up. And so in order to maintain the magnetic field that was already there, we're going to have an induced field that's pointing downward. So the induced field must be down. So we take our right hands, we put them down, and we see that that is a clockwise current. So Lenz's law tells us that in order to have, that if we have a changing magnetic field, that's the only time we're going to get a current, and that induced current will go in the direction that will oppose the change in the magnetic field.